Okay, today I'll be doing the third practice problem for homework number 6. I've already got things a little bit started here. So you see, I've restated the problem. Specifically, we have some object. We don't know what shape it is, we just know it's an object. And we know the surface temperature of the object is 400 Kelvin. We also know the heat flux from the surface is 10,000 watts per meter squared. This object is currently in a stream of air that has a constant velocity of 25 meters per second and is at a temperature of 300 Kelvin. We also know that the characteristic length, or the length from the front to the end, is half of a meter. So that's our case 1. We also have a second case, where now we have the same shape of an object, but it's now 5 times longer, 2.5 meters long. And the air, likewise, is slower. It's going 5 meters per second instead of 25 meters per second. The temperature of the air is the same, 300 Kelvin. The surface temperature of the object is the same, 400 Kelvin. We've been asked to find the convection heat transfer coefficient for case number 2. Okay, so let's discuss the approach we're going to take here. Whenever you see two similar shaped objects and things are changing, like the shape, the length, or the velocity, then you know that this is a dimensionless parameter type problem. And we're going to use dimensionless parameters to equate these two scenarios and use h for case 1 to find h for case 2. So we'll just say we're going to use dimensionless numbers. And then we're going to use h1 in order to find h2. So let's do our analysis. A good dimensionless number to start with is the Reynolds number, which for characteristic length L is equal to velocity times characteristic length divided by kinematic viscosity. Okay, so for case 1, we know the velocity is 25 meters per second, and we know the characteristic length, which is half of a meter. And we don't actually know the kinematic viscosity. We could look it up for air at that temperature, but we're going to leave that for now. So that's for case 1. For case 2, we also write the Reynolds number as velocity times length divided by viscosity. Well, our velocity has, let's see, decreased by a factor of 5, but our length has increased. It's 5 times as long. Okay, now for the same fluid, because remember this is air at the same temperature, which means our viscosity for both cases will be equivalent. Now 25 times 0.5 is equal to 5 times 2.5. What this tells us is that the Reynolds number for case 1 is equal to the Reynolds number for case 2. Okay, that's a cool result that tells us that we have dimensionally similar cases, at least from a velocity boundary layer scenario. So now let's figure out a few more things. Specifically, because the fluids are the same again, and because the temperatures of the fluids are the same, we can also say that the Prandtl number of both fluids are the same. What this tells us is not only is the velocity boundary layer going to be similar, but also the thermal boundary layers will be similar between the two scenarios. Now this is helpful because the average Nusselt number for a characteristic length is a function only of the Reynolds number and the Prandtl number. You'll remember the Nusselt number is a dimensionless number that corresponds to convection heat transfer from a surface. It's very similar to the friction factor, the coefficient of friction that you might see with drag on a surface. The Nusselt number is equivalent to that, but instead of drag, it's heat transfer. Okay, so because the Nusselt number is a function only of Reynolds and Prandtl, because the Prandtl number is the same for our cases and the Reynolds number is the same for our cases, then we can say that the Nusselt number for case 1 is equal to the Nusselt number for case 2. And that is actually very helpful because the Nusselt number averaged is equal to, let's say for case 1, the average convection coefficient times the characteristic length divided by the K of our fluid. And since our Nusselt numbers are equivalent, then we can also say that this grouping is equal to our convection coefficient for a second term times that characteristic length times the thermal conductivity. This is what we're looking for. Okay, so plugging in numbers, we can just find that the convection heat transfer coefficient for case 2 is just equal to 0.2 times h bar 1. So now we need to find what h bar 1 is. Well, we were given the heat transfer from the surface. So we could say, well, Q for case 1 is equal to H1 times the area times the difference between the surface and the surroundings. Okay, rearranging, we get that h bar 1 is equal to heat transfer divided by area divided by a temperature difference. Well, heat transfer divided by area is heat flux. That we were given 10,000 watts per meter squared. And we're also given temperature terms, 400 for the surface, 300 for the fluid. When we plug all those in, we get 100 watts per meter squared Kelvin. So now all we have to do is say, well, h bar 2 is just 1/5 of h bar 1, which is 100. So 1/5 of 100 is 20 watts per meter squared Kelvin. Okay, there you go.